Hello, welcome to this Learn tutorial on recursion. In this tutorial we're going to start off by telling you what recursion is, how it works, and then we're going to go through some examples and we're going to work through some Python code, and I'll put a link to all the Python codes on the YouTube video so that after the video, if you want to, you can go off and have a play and really get to grips with what recursion is and what's going on behind the scenes. Okay, so let's get started. So, what is recursion? Well, it's the use of procedures that call themselves in order to solve a problem. And the whole thing behind it is that you have a procedure, you give it a name, and then somewhere inside of that procedure definition, where you run all the rest of the code, it calls itself, it refers to itself. We'll show you what that means in a minute, it'll be pretty obvious. But although it looks quite simple, it makes it incredibly powerful. I'm going to show you some examples in a bit about how you can use that simple trick and it will solve many problems. Now, these problems usually stand out. They're normally difficult to solve using iteration alone. You can look at a problem quite often and go, recursion is the best option here. Not always. Sometimes, there's lots of different factors to consider. And you might want to try both iterations, depending on what the problem is, but it's another tool in your toolbox, and a very powerful tool. Now, each recursive call of a procedure, the important thing about recursion is that it breaks it down into smaller parts. So the idea is that through calling a function in itself, you're taking a bigger problem and breaking it down into smaller and smaller parts that you can't solve, until you can solve the smallest version of the problem, and then it comes back up solving the bigger problems from that smaller problem. So for instance here, when you're drawing a tree, it draws a branch, and then a smaller branch, and then a smaller branch, and it keeps going all the way down until it's drawn the smallest branch, and it reaches the end, which is known as the base case, when you've reached the base of the end of recursion. And once you've received the base case, it then comes back out. Okay, so what we'll do now is we'll start with the hello world of recursion examples. Pretty much every tutorial starts with this because it's a really great example. It's really simple, and yet it shows you what's going on. So in this example, we're going to calculate the factorial of a number, and factorials are really easy. All you do is to take the number that you want to calculate the factorial of, and then you multiply it by all of the positive numbers, positive integers below that number. So if our factorial is 5, we go 5 times 4 times 3 times 2 times 1. And the answer will be 120. So let's look at how we can solve that using recursion. Well, we can do a recursive function here. We've got the name of it, which is called factorial, and it takes the number 5 as an input parameter, or whatever you're going to put it. I've actually run it as 5 there at the bottom. And then it does this bit here. And all it does is it does 3 things, which I've broken it down to here. First of all, in order for a recursive function to be successful, it must stop when it reaches the base case, the simplest case. And in this instance, with the factorial, we know that it keeps on multiplying until it gets to the number 1, and then it stops. So what we do here is, in our definition, we say, okay, if we reach the number 1, we stop, and we go back, we return. And we'll look at how that works in a bit. Also, the function, it must move towards that base case in whatever it's doing. And there could be multiple base cases, and we can look at that in a bit about different base cases. But it must move towards one of a number of base cases. So for instance here, we can see that by doing n minus 1, each time the function calls itself, it calls itself with a smaller number. So the first time it runs on the outside here, it runs with 5. Then when it goes inside, it goes 4, 3, 2, 1. And then it stops because it's reached the base case. And the final rule for recursion, as you can see here, it must call itself in a recursive manner. Well, it does it here. There you go. You can see it's calling itself. Its name is factorial, but it's calling itself inside it. And it will keep calling it until it gets smaller, 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 reaches the base case, and then it will come out, which we'll show you. So before we do that here, let me show you using an online tutor that's really, really useful. Again, I'll put all the links to this in the comments. And here you just put your code in on the previous page, which you can't see, and then you can just run it step by step. So first of all, it gets this bit here, and it calls the factorial function, creating a factorial function object there. It runs it, and this is the first frame on the stack, this factorial function. It's the first frame, and its input parameter n is set to 5. Then as we go through, we haven't reached the base case, so we go through, and then we reach this point where it takes the 5 that it was given, and it runs the function itself again inside itself, but this time 5 minus 1, which is 4. So then it goes and adds another frame to the stack. Here we go, 4, and it keeps on going. It keeps adding it, and it keeps moving towards that base case until finally, there we go, the final run through. It's now reached the base case of 1, which means now what will happen is it'll start returning. There we go. Now when it returns here, it will return out of this function. So this bit here is going to be replaced with 1, and then it's going to be multiplied by the n value of the one above it. So here, this frame here is 2, so it'll be 1 times 2, which is 2. There you go, returns 1, hits there, it's now got 2. This function then returns, multiplies 2 times 3, returns to 6. 6 then returns, again, gets put back, multiplied by the 4, which returns 24, and then finally all the way back to 120, the final return value out of the function, returns back here, and it passes it to this result variable here, and there you go, result is 120. So let's have a look at how that happened. And again, I would suggest that you have a look at this rather than just watching the video. Play this code inside of the visualizer and you'll see what's happening, but let's just talk through it. So here's the main module. When we run the program, it stacks on top. It adds the first call, which is the n equals 5, adds another frame to the stack. By the way, each bits, these ones here, these boxes are called frames, and this here is the program stack, and it's called a stack because it's what's known as first in, last out, which means this one at the bottom is the last one to be removed, and you always take things from the top of the stack. That's how the computer is able to handle recursive functions. What it does, every time a recursive function is called, it creates a new area in the memory, which is called a new frame, and it adds that frame to the stack, putting it in that area of memory. So 5 goes to 4, creates another frame as it's going inside itself again, another frame, it goes inside itself again, and then it reaches the top here, the base case. We know that because there, if n equals 1, it starts to return. It doesn't recurse anymore, and then it starts to pass the return values back down the stack. There we go, return 1, return 2, return 3. It will do this. You don't have to actually return values. You could just put return, and we'll look at that in a little bit. You could just return from the function, but this particular function, because we're using these return values to multiply them by their parent values, then we need to return those values. There we go, return 24, return 120, and it goes all the way back. There we go, so it goes all the way up, all the way down. And you can see that now. Let's just do through that quickly. You can see here it goes all the way up and then all the way down. Now, when recursion happens where it goes straight up and then straight down, that's known as linear recursion because it just goes in a straight line up and then straight line down. Again, each of the contents of the stack will pile on top until it reaches the base case, and then each of the pieces of the stack are removed for each of the frame and remove one by one all the way down. So this is known as linear recursion. It's not the only type of recursion, and you don't always go straight up and straight down the stack. In fact, things look quite different in other examples. And this happens when a function calls itself recursively multiple times. So let me show you an example here. So here we've got another recursive function called drawTree, and in this recursive function here, drawTree calls itself twice. The first time, if it only had one, it would simply be linear recursion, but since it draws itself twice, this creates tree recursion, and it creates a very interesting setup. And we've used Python Turtle. Again, you can look at all the code to show you what actually happens, because it doesn't move straight up and then straight back down the stack. It starts to move in a very different manner, and it starts to go up and down the stack and actually starts adding frames to the stack and taking them away. And if you look now, there we go. If I let me put a time.sleep of 1 second on there. Again, you can mess with this if you want. So here you can see it goes recursive, 1 on the stack, 2, 3, 4, 5, 6, and now it takes one off and goes back to 5, and then back to 6, 5, 4, and then back to 5, 6, 5, 4. So this creates a very different form of recursion. And this here, it's a very simple example. I'm not going to sit here and watch all of it. You can have a play. Try changing all the branch lengths and things like that. It's a really great tool to visualize recursion. But the thing to take from this is that this type of recursion doesn't go straight in and then all the way straight back. It sort of does this little dance where it goes in and out, in and out. And in this particular manner, there's only 2 pieces here, so it's kind of a binary tree, really, because there's only 2 sub-branches for each branch. Depending on how many times you call it recursively, that will tell you how many branches off it goes. So this has only got 2 calls, so each branch will be split into 2 sub-branches. Now, again, thinking back to the rules of recursion, it works in the same way. It needs to have a base case, and the base case here is it stops when it reaches the minimum branch length. So if the size is smaller than or equal to the minimum branch length, then what it does is it stops. So it must have a base case. There it is. It must work towards its base case, which it does here, because each time it calls it recursively, it takes whatever the size it's just been given, which the original size was 140, and it divides it by a certain amount. I've put 1.8 here because I want them to get a little bit smaller each time, but you could quite happily just change that to any number you want, and it will just alter how many sub-branches in the tree, how small they get. But you can have a play with that. Okay, so tree recursion, this particular example is nice and pretty, but tree recursion is actually incredibly powerful. And I'm going to show you a couple of examples where tree recursion is used in normal programming use. So let's have a look. Let's say that we want to create a program that generates all the possible combinations of characters for a certain number of characters to a certain limit. So let's do a quick demonstration of that. Here's one I wrote earlier using for loops, and this program, all it does is it takes the characters A, B, and C, and it generates all the possible combinations using those 3 up to just those 3. So 1, 2, or 3 letters. You're not going to be repeating any letters. So there you go. That's nice and simple. And to write that in a for loop isn't too difficult, really. You can just do some nested for loops. So here we go. So for A, B, C here, and all it does is print them out. Well, that's fine. And that works perfectly fine. If you want to add more characters to it, then you can just add more characters. and then you can run that program again, and it will generate all of the possibilities for all of those characters in those the 3 character limit. But what if you wanted to do more than 3? So let's say you want to generate all the possible combinations up to a maximum string length of 6 characters. Well, what do? Well, this is where for loops get a little bit difficult, because what you're going to have to do here is you're going to have to then sort of cut and paste here. That'll take it up to 4, which is okay, and then let's do it again up to 5. Hit that again, and let's do that one more time. I think you can probably start to see where the limitation of things are here. There we go, where things aren't going to be brilliant. And already you can see, well, hang on a minute, A, B, C, D, E, F. It works, I'm sure it'll work. Let's have a look, let's just run that through, let's see if that works. Whoop. Oh no, D in charge. What's happened there? Oh. Let's just move that back. There we go. And as you can see, it's working through it, and it will probably, in fact, actually, probably what I need to do. Oh, that's because I need to print out the other characters as well. D, E. Oh, there's going to put D on there, and then D, E, and then D, E, F. Already you can see it's starting to get quite unwieldy. It does work, so it's generating all the possible permutations. I'm not going to stop until it goes all the way through, but you can see it's having a go. But this program is getting a bit unwieldy. Surely there should be an easier way of doing it. Well, yes, there is, and this is where Recursion really comes into its own, because to implement this sort of program in Recursion, all you do is you just create your character list as you did before, add any characters that you want to put in, and then you can just create a recursive function. So again, it needs to have a base case, which we've got here. We've said, okay, stop recursing when the length of the current string here is the same as the maximum length, which is 4. We'll put that up to, we can put that up to 8 if you want to. And if that's your base case, it then needs to work towards that base case. So in this instance, it's when it gets big enough that it equals 4. So what we're going to have to do here is for each recursive call, we're going to have to make this string longer, and each time all we do is we add a letter to it. Which letter we add to it? Well, we use this for loop here, and we're going to talk about that in a moment. So it works towards the base case, and it calls itself recursively, as you can see here inside of it. Now we know it's tree recursion because inside of the function, this function here is called multiple times depending on which character it is in the string. So in this particular instance, this for loop here would run 9 times. So for each outer branch, it would have 9 sub-branches all branching off. Let's just save that, and that will work here. Combinations of recursion. There we are. Hey, there you go, as you can see, and there it goes, off it goes. I've actually, what have I put in? I put a sleep in there. Let's get rid of that sleep because it's going a bit slow. That was just demonstrating, but you can see here that it's going through all of them. I put a sleep just to show you working nice and slowly. But if I kill that program and then run it again, there you go. It will go through all permutations. And the real advantage of this program is its simplicity. If I want to change this for 100 characters and I want it to be a maximum length of 50, then I just change those 2 variables, and then the whole thing just does it for each of those. This would have to go 50 times. Now, I'm sure there is also, there will be a way that you can use while loops and maybe use an array and things like that to implement this without using for loop, without using recursion. But look at that, nice and simple. In fact, let's see that working now. There you go. Look at that, boom, and it will just keep going through until it's all done as much as you like. There we go. There we go. Good, brilliant. So that is the combinations using recursion, and as I said here, it is a form of tree recursion. And if you don't believe me, well, let's just have a look at it in the tree recursion. Here we go, and we'll just run it. Here's one. Again, you can have a look at it. I'm not going to talk through this code here. You can have a play with it, but you can see the general gist of what's happening. It's going to show you how this tree recursion works with a few letters. There you go. There we go, brilliant. So there it is, there's tree recursion using these combinations, converting all the combinations. And you can see this tree in action. It really helps to visualize what's going on. The first time it runs through inside of the recursion, it goes inside, it branches off to the A, branches off to AA, branches off to AAA, and the maximum length is 3, so therefore this is the base case, so it doesn't recurse any further. It then goes back. Of course, this isn't then the base case, and it goes up and then back and then up and back, etc., etc., working its way through all of the recursion. If you want to have a play with this, you can change this, you can change all that. I chose those because it seemed to make sense. You can actually add as many as you like, but you can see that it does work. It will work for all the combinations you give it, and that is the real power of recursion. The program is easy to write. It's generally much easier to look at. Although, especially when you first start, if you don't understand recursion, you're not sure about it, you haven't had a lot of experience, it can be quite daunting. Okie dokie. So I've just got one more thing to show you and it talks about the stack here and how each of the frames, when you're doing tree traversal, recursive tree traversal, how the stacks work. Now you've probably guessed it here. You've got a frame, and then another frame, and then another frame, then another frame, then another frame, and then it removes a frame, and another frame gets placed on top. But what we'll do is we'll just show you that here using the online interpreter, this step-by-step one, and we'll just run through it just quickly. So it keeps adding until it gets through to 3, because the maximum length I've chosen here is 3. So here we got 1, 2, the main global frame, and then here are the subframes. They're all stacked on top. As soon as this last frame is stacked on top and it's done with, we then go back, out, there we go, return none, because we're not actually returning anything. Like I said before, you don't have to return something. And then it goes away, and then another frame gets replaced. It moves on to the next letter, gets placed on top, comes back through, goes through the C, and now because it's exhausted the ABC here, it will then drop back up to this frame and move this second letter from an A to a B. There you go. There you go. Comes back. There we go. And then it changes that letter to a B, and then it adds more to the stack here. This stack's upside down. Normally you think of stacks from top to bottom, but it's just the way that this interpreter works. Okie dokie. So let's have a look at one last example of where tree traversal can be used. One common example. And tree traversal in recursive tree traversal, one everyday application is traversing files and folder systems. So what we've got here actually is we have an algorithm here, a program that will allow you to traverse every file and directory inside of your computer. So if you imagine your directory, your C drive or whatever you're using on Linux, it starts off as a single drive and then it breaks into folders and then subfolders and then subfolders, and that just, it goes through, this program can look through all of those folders. Now we know it's tree traversal because A, it's looking through all your folders, but B, here, the print files is a recursive function, and here you've got a for loop. That means it's going to go multiple times and split down, and it's going to run the same function. Here you can see it. It's going to run the same function, but it's going to run it recursively a number of times. It will keep doing that, and it will keep doing it until it reaches this bit here where there are no folders. If there is no directories, if there's no folders here, then we've reached the base case, which is there's no subfolders to go into, at which point it will start going back up through the tree. Now, it's interesting because this is searching through your home directory and through your hard drive, then it isn't going to be it's not going to have an even number of branches inside that splits off from each branch. So you could have your main C drive as your first branch, and then it could have 50 branches, and then 12, and then 10, and it will just go through it. But because it just goes through the whole directory list and tries to go into the subdirectory, it doesn't matter. It will just run itself recursively. And this sort of algorithm here is incredibly powerful and incredibly common. It's used for all sorts of things. If you want to search for a file, you can use a modified version of this to search for a file. If you want to calculate the size of all the directories and all the files in directories, then you can use this to do that. So let me show you that. It's called some recursive dir. So Python recursive dir. There we go. There you go, and you can see it. There it is. The program's running, and it's just going and it's showing you each of the branches in the tree. Now this tree setup here, it's just showing each little branch, and then it comes back, and you can see it's just going through all the way through my lovely little file system. There we go. I'm not going to show you that because we'll be here till tomorrow. Okie dokie. So that's just another practical example of where recursion is actually used. Obviously, when you're learning recursion, we use things like factorials, and we use the factorials examples, partly because it's easy, and partly because this is really likely to come up on any exam or test that you do. Factorials or the Fibonacci sequence, those another example that can be used recursion. They're really, really common. But tree reversal, the very common form of recursion, this is used widely. So, for instance, I showed you it uses file structures, but it's also used for scraping and parsing web pages and brute force hacking of passwords. I'm sure it doesn't take a genius to work out that a modified version of this sort of algorithm here could be used for a brute force attack. And it's used for things, all sorts of different things, like the shortest path maze navigation. So just a recursive approach to searching through mazes. Let's try this path. Okay, let's go this. For each subpath, each branch off, you go and check down it, and you just do that until you find the solution. So there we go. And just to conclude, here we go. So finally, why do we use recursion? Well, some problems which otherwise would be really difficult to solve can be easily solved with recursion. It reduces the complexity, or it can reduce the complexity of code, as we saw within the for loop alternative example. And it's great for certain things. It just works really well. For instance, anything that involves tree traversal. But it's not, it's not a solution to everything. Recursion is memory intensive, and the reason it's memory intensive is for every recursive call, it's got to allocate a new area in memory. In fact, most programming languages have a limit on the size of the stack. For instance, Python, if you do 1,000 recursive calls and the stack stacks up to 1,001, then Python will actually throw an error and it will crash, and it will say recursive depth limit reached. So you've got to be aware of that. It doesn't solve all problems. It may also be slower than non-recursive solutions, so you're going to be aware of that. Try both. Or it could be just more difficult to program. And especially for beginners or for somebody who isn't unfamiliar with that particular program, then it can be difficult to read and especially difficult to debug because you don't looking at it, you don't always know, you can't always see whereabouts you are inside of that recursive call. You don't know how many recursives deep that you've gone. So that can be difficult. Okie dokie, so that's all done. What I would advise you to do is go have a look at those links, have a play with them, tinker with the code, change it, try your own things. If you did like the tutorial, then please feel free to like and subscribe. And other than that, thank you very much.